Here we've been talking about nuclear chemistry, and we got into, I think, balancing equations last time. And remember, when we balance an equation, nuclear chemistry is a little bit different than a normal equation, a chemical reaction. Basically, there's two things you got to make sure of. Mass number on the left equals all the mass numbers on the right, and our atomic numbers there on the left equals all of our atomic numbers there on the right. Remember that it is the atomic number there that's going to probably allow you to figure out maybe what is missing. It could also be a particle. So we saw several different sort of particles that are used, like neutrons, obviously beta particles, positrons, alpha particles, and so forth. Remember that if something is emitted, if something goes through some type of decay process, again, those particles will be over there on the product side. If something is sort of bombarded or like an electron capture, those guys will be on the reactant side. We also talked about radioactive decay for most part there last time. Radioactive decay will always follow first order kinetics. And really with first order kinetics, you got pretty much two equations that go with that, which is one version of it, natural log of A, natural log of A naught minus KT. This again is sort of like your final, either concentration, mass, whatever it may be. Also, we saw we could use like radioactive decay, like counts per minute or disintegrations per minute. Here is your initial. This is the rate constant in kinetics, referred to usually as the decay constant here in sort of nuclear chemistry. And a reminder that T here is time, so not temperature or anything like that, but it is time. We also talked about that you do want to watch the units on these two, make sure that they are obviously in the same unit of time. In addition, as we saw in a number of examples we did the other day, we oftentimes will have to use the half-life equation to help us sort of solve these guys. And for a first order kinetics, the half-life is the natural log of 2 divided by K. And again, the natural log of 2 is 0.693 when you do that divided by K. So as we saw, a number of times, you'll probably kind of use the half-life equation to solve for the decay constant by doing this. And then obviously when you get that, you could go into the other equation, solve for whatever you may be looking for. We did some sort of dating type problems. So we solved for time in those cases. And then obviously on some of the other ones there, we solved for, how much was left over in terms of mass and how much counts per minute was left over in terms of radioactive decay. Any questions on any of that kinetic stuff there? Okay, so the next thing we're going to talk about then is mass defect and what is referred to as binding energy. I feel like I missed a slide there. It just went away there. All right, we'll go that way, I guess. So, yeah, like a slide is missed there, was it? Guess not, maybe not. There it is. I went ahead of it. My bad. So we'll start with that. I think that's the next one that comes on your handout there. All right. So where does the energy from fission come from? Remember, fission is sort of the breaking down of a nucleus or an unstable nuclei into new nucleuses. It usually will occur a lot of times when it becomes unstable. It will sort of split off into really two new nucleuses. It will also usually produce some neutrons as a result of that as well. And it will also give you a lot of times energy that sort of comes out as a result of that process. So this can happen sort of spontaneously. It can also happen by basically forcing it to happen, where you sort of bombard a sort of stable guy with some type of particle, hit it with a neutron or something like that, it will become unstable and it'll sort of go through this process. So during nuclear fission, some of the mass of the nucleus is actually converted into energy via our Einstein equation here, equals mc squared. In this case, the mc squared part here, the m is what we refer to in this case as the mass defect. The mass defect is basically the difference in the mass that makes up the nucleus, so that's your protons and your neutrons, and sort of the mass of the isotope itself. So there's a slight mass difference that gets kind of converted into energy during this process. Obviously, c is our speed of light, which is 3 × 10⁸ meters per second. So this is one way that we could kind of calculate what is referred to as binding energy, as we'll see in just a second. But as a comparison, each mole of uranium-235 that goes through fission will produce about 1.7 × 10⁻13 joules of energy. And that is a lot of energy just being produced. If you compare it to like a super exothermic reaction, it's producing like 10⁶ amount of energy. That is why they would use fission reactions in nuclear power plants. It generates a lot of heat and a lot of energy in that process. So that is sort of the reaction that's used in like nuclear power plants to sort of power them, obviously, as opposed to traditional power plants. So now that we've got that slide, let's talk a little bit about that energy. So the mass defect and binding energy. So when a nucleus forms, as I mentioned, there's some mass of the separate nucleons. And remember, nucleons are our guys in our nucleus. So that's like your protons and your neutrons. Is converted into energy. And again, it is converted into energy using E equals mc squared. The difference between the mass and the separate nucleons and the combined one is known as the mass defect. The energy that's released when the nucleus is formed is sometimes referred to as the binding energy, or sometimes the nuclear binding energy. There are a couple of kind of conversions here that basically come from here that you could sort of use in place of using E equals mc squared. So you could actually use E equals mc squared, or you could use a couple of these conversions without having to necessarily go into that equation. One is 1 mega electron volt is equal to 1.602 × 10⁻13 joules. And 1 AMU of mass defect is equal to 931.5 mega electron volts. Now, we talked about stability earlier with our sort of neutron to proton ratio. This is another very common way that we look at stability, which is basically the binding energy per nucleon. And the higher the binding energy per nucleon, the more stable that nucleus is. So let's take a look maybe at one here. So let's say we had fluorine 19, and it has an atomic mass of 18.9984 AMU. And let's say we wanted to calculate the nuclear binding energy by doing this. We would obviously look at fluorine 19, and we would see that it has 9 protons, right? And if we subtract 19 from 9, gives us 10 neutrons in this case. So to calculate the mass defect, what we would do is basically take the 9 protons, and we would times it by the atomic mass of a proton, which is 1.00785 AMU. So this is the atomic mass of a proton. We would then add it to the number of neutrons, which is 10 times the atomic mass of a neutron. These are really the components, right, that make up this guy, the nucleus there, which is 1.008665 AMU. Again, this is the atomic mass of a neutron. We would then subtract it from the atomic mass of this particular isotope, which is 18.9984 AMU. And if we do that, and I reset my calculator, there we go, 9 times 1.007825 plus 10 times 1.008665 gives me 19.157, subtracting 18.9984 gives me a mass defect of 0.159 AMU. So this would be the mass defect. This would be basically the difference in the mass that's going to be converted into energy. So at this point, you do have two options. So let's look at both ways you could kind of get to the same answer. First off, if you wanted to use Einstein's equation here, you could go into E is equal to mc squared. Again, the m would be our mass defect here. And if we did that, we would have 0.159 AMU. We would times it by 3 times 10 to the 8 meters per second. We want to make sure we do square it at that point. So taking this number, times it by 3 to the 8 squared gets us something like 1.43 times 10, looks like 16, I think. AMU is the units times meter squared divided by second squared. Any questions so far on that? Now, we can do a little conversion here to get it into a unit of energy that we like, which is a joule. And you might remember that a joule equals a kilogram times meter squared divided by second squared, which means we're very close. We just need to get rid of the AMU there. So if we take 1.43 times 10 to the 16 AMU meter squared kilograms, not kilograms, but second squared would be good. Second squared. And we do a little conversion with a number we're sort of familiar with. How about 6.022 times 10 to the 26 AMU per kilogram? Avogadro's number is to the 23rd, yes? That gets you grams, right? Kilograms is 1,000-fold bigger, which is why it's to the 26 here to get us to kilograms, yeah? So the AMU will cancel. And if we take that number and divide it by that, gets us 2.377 times 10 to the minus 11 kilograms meter squared second squared, which is the same thing as a joule. So basically that would be the energy in joules. Any questions on that there? Now, a lot of times, well, the way that we present sort of binding energy is binding energy per nucleon, which means we would take this number, 2.37 times 10 to the minus 11 joules, and divide it by our nucleon, which is basically our mass number. And if we do that, we end up with 1.25 times 10 to the minus 12 joules per nucleon. Any question on that calculation there? Now, that is one way that you could solve these problems, by sort of using Einstein's equation, using Avogadro's number there to do that conversion. You could also use those other values that we saw there, and you can use those conversions to do it. So let's take a look here and see. We'll go this way, I think. We will pick it up with our AMU. That was 0.159 AMU, which was our mass defect. And if we did that, we could go 0.159 AMU. We could use our conversion factor that we saw on the previous slide, that 1 AMU is 931.5 mega electron volts. Those guys would cancel. And that will get us about 148.1 mega electron volts. We then could use the conversion factor if we want. By the way, this is a unit that they also use for binding energy. So if we wanted to, since we're here, we could divide this by 19 and we'll get our mega electron volts per nucleon, which is about 7.795 mega electron volts per nucleon. We also can convert it into joules by using our conversion, which is 1 mega electron volt is 1.602 times 10 to the minus 13 joules. And now I got the wrong number there. I punch that in. Ends up with 2.37 times 10 to the minus 11 joules, which I hope is the number we had on the previous page, was it? That's good. At this point, we once again could divide this guy by 19 and gives us the same number, hopefully, of 1.25 times 10 to the minus 12 joules per nucleon. So this way sort of bypasses using Einstein's equation. They kind of come from Einstein's equation, these conversions basically. And you can see you get the same answer. Either way is up to you. These will probably be provided for you, these two conversions. So if you like that route, you could go that way. Or again, you could do it the other way as well. These are, again, two very common units of binding energy, mega electron volts per nucleon and joules per nucleon. And again, we could use those values, the one that is per nucleon, as a measure of stability. If you're comparing to sort of isotopes and you calculate the binding energy for both of them, the one that has the higher binding energy per nucleon will be more stable than the one that is obviously less. Any questions on either of those calculations? All right, then here is a chart of some binding energy per nucleon versus mass number. And what we see is actually our good friend iron 56 is actually the most stable. It does have actually the highest nuclear binding energy per nucleon. And as we've been talking about, obviously, more stable, the higher number you got. In case you don't like that first graph, you can look at this graph. And most stable nuclei fall in that sort of iron range. And then as you sort of go past it, it starts to trail off in terms of stability. So why don't you try one here, calculate the mass defect and the nuclear binding energy per nucleon in mega electron volts. Why don't we also do joules? Just do them both per nucleon and also mega electron volts per nucleon. For carbon 16, and again, I don't think you have the numbers there. You don't. So let me write them in. The proton's mass is 1.007825 AMU. Neutron's mass is 1.008665 AMU. And obviously carbon is lucky number 6 there, right? Carbon is 6 on the periodic table. I think that should be everything you need. Give it a go, see what you come up with. Okay, let's take a look, see how you're doing. So obviously 16 is our mass number there. So it does have 6 protons. And obviously if we take 16 minus 6, gonna give us 10 neutrons. So obviously that's gonna be important to figure out our mass defect. So we could do that up front here. Our mass defect, which is, again, sometimes used as an M. Sometimes people in some books will use it as like a little triangle to represent mass defects. So sometimes see that as well. Yeah. What's that? No, it just happened to be, I think, these 2 examples. It came to 10 neutrons, but you want to use whatever neutrons are in that particular isotope. So you want to take the mass number minus the atomic number. I think it's just coincidence in that case. But sometimes, again, you'll see sort of Einstein's equation also written sort of like this, with that little triangle. So we're going to take our 6 protons and we're going to times it by the atomic mass of a proton, 1.007825 AMU. We're going to add it to our other member of the nucleus there, which is our 10 neutrons times the mass of a neutron, 1.008665 AMU. We're then going to subtract it from the atomic mass of the isotope, which is usually given to you, and that is 16.014701. That's a lot of numbers. And if we do all that there, 6 times 1.007825 plus 10 times 1.008665 because it's about 16,133.6 minus 16.014701. There we go. Going to give us something like 0.1189 AMU as our mass defect. Once again, going to be sort of the mass is going to be converted into energy during this process here. And again, you can use Einstein's equation, but since we're doing mega electron volts, maybe just using the conversion might be an easier move. So we will go with that. So 0.1189 AMU. And using that 1 AMU is 931.5 mega electron volts. That is going to get us here about 110.8 mega electron volts. Since we are looking for it per nucleon here, and we're going to divide it at this point, since I have the number right there, I'm going to divide it by our nucleons, which essentially protons, neutrons, our mass number, basically 16 nucleons. And that will give us our answer for mega electron volts. I didn't round the number on my calculator, so I ended up with something like 6.922 mega electron volts per nucleon would be one of the answers, obviously. At this point, I can either take the number I just boxed or the previous number and use the conversion to go from mega electron volts to joules. So I'll just take the final number there, which was 6.922 mega electron volts per nucleon. And at this point, I could just use my to joules conversion there. 1 mega electron volt, 1.602 times 10 to the minus 13 joules. Again, these guys are going to cancel in this case. And we will end up with 1.602 to the negative 13. We'll call it 1.11 times 10 to the minus 12 joules per nucleon. Any questions on any of that calculation there? If you went Einstein's equation, you would end up with joules and then did the conversion to mega electron volts. So you'd just be kind of going the other way. Any questions on any of those there? Okay, so let's try one more here. So I think you got iron coming up next there. So calculate the binding energy per nucleon. We'll do both again, so we have them to compare in a second. Do a mega electron volts per nucleon and also do the joules per nucleon as well. And once again, proton 1.007825. Neutron 1.008665. And our good friend iron is lucky 26, I think, on the periodic table there. Okay, let's take a look and see. So again, from the atomic number, obviously we know we got 26 protons. Taking our mass number minus our atomic number lays us up 30 neutrons. So we'll start with our mass defect again here. And we're going to take our 26 times our 1.007825. We're going to add it to all of our neutrons that are there, which is 30 times 1.008665. We're then going to subtract it from the atomic mass of the isotope there, which is 55.93494. Too many numbers. All right. So 26 times 1.007825 plus 30 times 1.008665, subtracting the 55.93494. There we go. Gets us a mass defect of 0.5285, we'll call it. At this point, again, you have the two options. So since I did the kind of conversions last time, I'll throw it into Einstein's equation this time again, so you can see, in case you like that way better. We're going to put that in as our mass. We're going to times it by the speed of light, and we're going to make sure that we do square it. And if we do that, gets you 4.76, I'll call it, times 10 to the 16. Again, here we're in units of AMU, meter squared, second squared. Here we would then basically divide by Avogadro's number to the 26 to get us to the right units here. Kilogram. And if we do that 6.022 to the 26, that gets us basically 7.898 times 10 to the minus 11. And that becomes joules because we are left with kilograms, meters squared, second squares, which is the same thing as a joule at this point. So since we do want it per nucleon, we're going to take that and divide it by 56 here to get us to our nucleons. So we divide it by a 56er, gets us a 141 to the minus 12 joules per nucleon. First off, any questions on taking that approach there? At this point, I can just take that final number now and just use the conversion to go to mega electron volts. And if I do that, we have 1.41 times 10 to the minus 12 joules per nucleon. And again, 1 mega electron volt, 1.602 times 10 to the minus 13 joules. That is going to cancel out our joules here. So gets us an 8.804 mega electron volts per nucleon. Again, give or take, depending on where you round it. Yes. Any questions on going this way? So again, if you can't find those conversions, which would be right on the paper, you can't find them, then you can still obviously use E equals mc squared. Any questions on that one there? So now we did actually 3 of them here. So let's just kind of take a look at what we ended up with in terms of our binding energy per nucleon. So our iron 56 here ended, and we'll just look at the mega electron volts, 8.804 mega electron volts per nucleon. Our other guy had 6.922 for our carbon 16. Carbon 16 was 6.922 mega electron volts per nucleon. And the very first one that we did there was about 7.795. 7.795 mega electron volts per nucleon. And that was for fluorine 19. Most stable here is which one? It is the iron 56, like we saw in the graph there, right? It was at the top, has the highest binding energy per nucleon, followed by fluorine, and then carbon 16 would be the least stable of those three based on binding energy per nucleon. Any questions on calculating binding energy? Okay. Let's talk a little bit about transmutation. Transmutation, you know, is kind of like when you throw something or shoot something at an isotope, it becomes unhappy sometimes. We could do a particle accelerator here. It's got a magnetic field and an electrical field. Basically, you get your particles spinning really fast. Then you shoot it at it. And in this case here, we got our nitrogen 14 hit with an alpha particle, making oxygen and a proton being released. And again, aluminum releasing a neutron. So usually when you do this, you'll create obviously a new element. It will oftentimes release a particle in that process. On the periodic table, everybody kind of past 93 there is a transmutation where this process occurs. They all basically got kind of be made by hitting something, particle at one of those guys. That's how we get all of our fun man-made ones like californium, einsteinium, berkelium, nobelium. So we take these guys, shoot a particle at it, and then it obviously will form these new guys. Obviously, as you can also see in the process of doing that, since we are changing what's inside the nucleus there in terms of protons and neutrons, they do release some of these particles along the way. Those are usually your bottom row there on the periodic table. So let's talk a little bit about fission and nuclear fission. This sort of transmutation process can also occur in a fission process here. So if we take something like uranium-235 here and we basically shoot it with a neutron, it becomes a very unstable bowling pin here known as uranium-236 perhaps. And basically this uranium will be unstable, so it's going to basically split off into two new nucleuses. And again, that's commonly what you get when you have sort of a fission reaction occur. And more importantly, it will also produce several neutrons in this process, and not to mention a lot of energy as well. So as I mentioned earlier, this is sort of the reaction that's used in like a nuclear power plant to help sort of generate power. And we can figure out the energy by taking basically the mass defect times Einstein's equation here, c squared. This equals mc squared, basically. And basically, in this case, we're taking our difference between the mass of what we started with and the mass of what we ended with, right? So that's the difference between sort of where we ended and where we started. And we get something like 2 times 10 to the 13 joules per mole of uranium-235 is the amount of energy that comes out. If you compare that to a combustion reaction of coal, 1 ton of coal, you get about 5 times 10 to the 7. So that is, again, a very big difference in terms of the energy. By the way, they compare it to coal because coal is also used to do what? To make power. Yes, so they burn coal basically to power a traditional power plant. Nuclear power plant does like a fission reaction to do that. So that's why they compared those two there in this particular case. As we talk about, it's not always going to be these two that will sort of bounce off and sort of be made. There are different sort of products that are made. There are sort of predictable ones that you might expect to be made, but it won't always necessarily be the exact same two that's made every single time. And that's what we see here. These are sort of the peak mass numbers that are commonly made in a fission reaction. So once again, you won't get exactly these two guys every single time it goes through that reaction, but you will get probably somebody in this region in terms of the mass numbers, and it makes these neutrons and this energy. This process can be problematic because part of the product that is made is the exact same thing that starts the whole thing. So that could be problematic, as it can continue to sort of go that type of reaction. And that gets us to what is sometimes referred to as a nuclear chain reaction. A nuclear chain reaction is a self-sustaining sequence of nuclear fission reactions. And again, the idea here is you're basically making neutrons, and that's sort of how you start the whole process. So you're kind of feeding and fueling this reaction as it goes through. Now, in order to sort of maintain this reaction to sort of go on and on and on, you do need what is referred to as the critical mass of some type of material like uranium that is able to go through fission. If you have non-critical mass, at some point, this reaction will sort of die down and won't be able to self-sustain it. If you do hit critical mass, you're just going to keep this reaction kind of going. And again, because we make these neutrons, which go back around basically and start the whole process again. And you kind of grow exponentially here, right? Every time you make it, you got 3 new neutrons, got some more energy being made every time around. And that can be a very bad thing, because a lot of the products made are obviously radioactive, right? So the byproducts of those things are also very much radioactive. Going with a nuclear bomb here. And when the bomb hits, obviously there's some explosives there. They do keep the fissionable material separated until it hits. Then the triangle fits in the hole, and now you have critical mass there, which obviously would kick off that fission reaction. Not very good results as a result of that. So this is really the same reaction that occurs in like a nuclear power plant. And power plants, by the way, all kind of work the same way. We just hit the light switch and hope for the best usually, but no. Pretty much you have water, and you heat up the water. Water, when you heat it, makes steam. Steam goes out to the turbines, and out goes to the generators, and you've got some light. By the way, since they do use water, they can also condense back down the steam back into water and keep the cycle sort of going on and on very well. The difference between a traditional nuclear power plant, I guess not a traditional nuclear power, the difference between a traditional power plant and a nuclear power plant is frankly how they heat the water. Yeah, so in a traditional power plant, they used to use coal basically, and they would burn coal. It obviously generate a good amount of heat. That heat would be used to heat the water, and off it goes, and you get some lights. In a nuclear power plant, they do basically a fission reaction, which generates a lot of energy, and they use that energy basically to heat the water. Same end result. This is sort of a cross section of a nuclear power plant. I think our closest, I don't think is working anymore, but it was San Onofre over there off the 5, I think. The 2 big domes as you drive off there by the beach. And they usually are put by a very big body of water, because they need water to kind of do this whole process. If they're like in a different state like Arizona, they have really big like cooling towers or water towers that they use for that. But inside, there's kind of 2 parts to it. There's a really shielded part where really the fission reaction occurs. And in here, there are what are referred to as fuel rods. And in the fuel rods, basically, there's like eraser-sized pellets of uranium. And that obviously is the source of the reaction that begins. The fission reaction begins, obviously, keeping all the radioactive part kind of over here. Runs a tube that goes through the big thing of water. Obviously, this is going to be very hot water at this point. That hot water is then going to heat the big water over here, which is a little bit away from the radioactive part, going to create this steam, and obviously out to the turbines and generators, and you get light. And like I said, a lot of times they will then kind of cool down that process and sort of regenerate that water, which is why they need a lot of water near them to kind of cool everything back down and get through condensation. So why does it not go out of control? Why does it, not do a sort of chain reaction? There are some safety things that they usually will do. They first off keep usually the mass below critical, so usually use a non-critical mass. of uranium, so hopefully the reaction won't go out of control. The other really important thing is they typically will have control rods in there. And control rods are these guys that are basically soaked in something like cadmium, which is a good neutron absorber. So why would something that absorbs neutrons be really good in this type of reaction? What starts this reaction? Neutrons. What is made in this reaction? Neutrons, right? Just can keep the reaction going. So you have these control rods in there that kind of grab out a bunch of neutrons in this reaction and thus kind of keeps it under control and so forth. And that's why, you know, not too many bad things happen occasionally. Except when they do like a safety test and they take out too many of those at once and can't get them back in, then, you know, you get like a Chernobyl kind of situation happening. So, you know, this is sometimes referred to as sort of clean energy in a sense. People think it's relatively clean, but you got to also think about there's a lot of nuclear waste, right? That's made in these processes here. And, you know, for a lot of years, they really didn't know what to do with a lot of that stuff because nobody wanted it in their backyard or wanted it transported from wherever it was going to past their house and stuff like that. So years ago, they started building a big thing in Nevada, I think, and they actually started using it, I think, that's recent years and stuff like that. But for a lot of years, everybody would kind of keep everything sort of on site as well. A lot of our nuclear power plants are kind of shut down. It's hard to keep them up to date and code and stuff like that. I believe both of the ones at San Onofre, I don't think are working anymore. I think they shut the last one down a number of years ago. So there are some benefits obviously to it, but there's also obviously maybe not so good benefits, and there's good and bad for both. A traditional power plant, obviously, when you burn coal, you put a lot of pollutants in the air besides the fact of ripping up the land to try to get to all that kind of stuff and get the coal. And then obviously a lot of nuclear waste is made. Where it's a lot of stuff that will stay around for a very, very long time, right? These things have half-lives of thousands of years, right? So it's like, who keeps an eye on it? What do you store it in? You know, so there's a lot of those sort of issues. Now, also another sort of problem, if you will, with nuclear fission type reactions is, like I said, what is sometimes referred to as spent fuel. And this is basically those kind of byproducts that are made as a result of these fission reactions, in addition to the starting uranium, which is, you know, going to be around for a long time. You get a lot of these leftover products that also are going to be radioactive and pretty hot for a long period of time. So again, sort of safeguarding that and keeping it safe is, you know, a major issue. Obviously, we do wind power now, right? And all those kind of things, right? Drive out to the desert, see all the windmills going around. Nuclear fusion, on the other hand, different than fission. Fusion is when we kind of take two smaller guys and put them together at like super hot temperatures. Like on vacationing on the sun type temperatures is when like fission happens. So those two guys come together, as we can see here, a couple of hydrogens coming together and making some helium. Again, a lot of energy is released, but usually does happen at very, very high temperatures. So that's the difference between fission. We have one unstable guy that splits off into two new ones and some neutrons under kind of normal temperatures. Fission, two small guys make a larger guy involving really hot temperature. That's why in all those spy movies, right, they're always looking for the guy that did the cold fusion, right, reaction. So to finish up here, talking about radioisotopes used in medicine, as we touched upon, there's a lot of obviously radioactive isotopes that's used in medicine. And clearly, if it is, you definitely would want something with a small half-life or short half-life. You don't want something that's going to be years and years down the road. So here's some examples. Obviously, sodium, there 24 is used as a blood tracer. Iodine 131 for some thyroid gland activity. Also 123 iodine there for some brain imaging. The nice thing about isotopes is, for the most part, they will behave in the body just like sort of the non-radioactive version of it. So the benefit, I guess, of the radioactive version is you could basically find where it is at any given time through a scan or monitoring the radioactivity. In labs, sometimes people will use radioactive versions of elements and stuff like that, and to follow where something goes. I used to do research where we use radioactive radioactive copper, because we were doing copper proteins. So by using a radioactive copper, we basically just follow the radioactivity and see basically where are the copper, what in the system along the way. Some technetium 99 there, some imaging agents. Obviously, there's a bone scan, and again, it will sort of highlight the areas, obviously, where those radioactive guys get into. But you can see a lot of the half-lives here are hours, and sometimes maybe minutes and stuff like that. You definitely would not want a very long half-life. If you ever do use radioactivity in the laboratory or anything like that, you will pick up one of these guys, which is a Geiger counter. And it's like got a wand that beeps and beeps. Point it at yourself, hope it doesn't beep too much, right, as you're doing radioactive work. Basically, a little reaction occurs there, anode cathode reaction, and sends a voltage over there to give you the beeping sound. More beeping means a lot of radioactivity, right? Less beeping and not so much. So usually you use it if you're working or if you just cleaned up an area to make sure obviously nothing is on there. If you are working with radioactivity, usually they will, years ago, and I think they still do, they used to give you a ring and like a little badge that you're supposed to be wearing as you're working with the radioactive stuff, to make sure they develop it every so often to make sure hopefully you're not glowing in the dark. They got too much exposure. If you do work with radioactivity, you should always, like I said earlier, make sure you understand exactly what type of emitter it is and sort of what safety stuff that you need to use. Because again, sometimes people don't tell you all those good things. If I hold up the Geiger counter just in the air, will it beep? It will. There's background radiation, right? So it will beep. That's the other thing you hear when the guy's doing it, like, just background radiation, don't worry about it, it's all good. So it will beep, if you just hold it up, hopefully not loud, but there should be a very small sort of background radiation that happens. Also, a good piece of advice is if you're working with radioactivity, always check your shoes before you go home. Yes. People drop stuff on the floor, you walk on it, you take it home with you. Yes. So that's a very common thing that sometimes people do. Speaking of just sort of background radiation, sometimes we measure it, biological effects of it, and what is referred to as a rad or a REM, which is sort of a man equivalent of it. But basically, there's all kinds of exposure we get in the ground and our surroundings, depending on how many x-rays and stuff that you take, air travel, if you happen to live near fallout and weapons testing, or if you happen to live near nuclear waste, I suppose, as well, you might pick up some as well. But to sort of figure out the effect on man, it is obviously multiplied by the type of emission that occurs. And as you remember before, the gamma rays, which is the top guy, right, does penetrate lead pretty far, and also is your tissue the farthest, followed by beta, and then alpha doesn't penetrate as far. So that's why alpha has a higher sort of factor there. You could kind of get hit with alpha particles a little bit more than you can gamma rays, right, without causing significant damage. But obviously, if you, I shouldn't say that, you can cause damage, you definitely don't want to be standing there getting just pelted by the stuff, but you want to limit your time as you're exposed to it, right? When you're doing things, sometimes that's easier said than done, and also make sure you are wearing the proper equipment. Any questions on any of that there?